In this video, I'll talk about another mechanism that causes the exogeneity assumption to fail, and this mechanism will be measurement error in a regressor. Our discussion will be based on an economic example where we study the relationship between ability and exam scores. Suppose that for a sample of students, we observe the variable score, and score gives the exam score in the econometrics exam. We also observe the variable IQ, and IQ gives the test score that the student achieved in an IQ test. We can regress score on IQ and obtain an estimated slope coefficient beta 1 hat. If we want to interpret this estimate as measuring a causal effect, then we assume that there's an underlying linear production process that describes how IQ produces exam scores. In this linear model, beta 1 describes a causal effect of IQ on score. But is it really meaningful to think of a causal effect of a test score in an IQ test on your exam score? The test score in an IQ test depends on many things. Among others, it depends on how lucky you got. So you may have just had a very good day or very bad day, and that may affect your test score on the IQ test. There is no reason to believe that the randomness inherent in the test score here affects the test score in your econometrics exam. Therefore, it is not really meaningful to write down a linear regression model like this that presumes that all components of your IQ test score affect the econometrics exam score. What we may have had in mind when fitting this regression is that IQ measures unobserved ability. Since the IQ test score does not only reflect ability but also random factor, it's not a perfect measure of ability, but it is a measure nonetheless, and it may be the best measure that we have. It is very plausible to assume that ability has a causal effect on score. So the underlying regression model that we've probably had in mind was one where we have score on the left-hand side, and on the right-hand side, we don't have IQ, we have ability. Ability is our variable of interest, and beta 1 in this regression model is our parameter of interest. So the situation that we have is one where we want to run this regression, but we don't observe the regressor. So we're replacing the regressor by a measurement. In that case, IQ is called a proxy variable. And we say that it measures ability or that it proxies ability. Then, since we couldn't run this regression, we ran this regression. Now, our hope is that the estimated coefficient from the regression that we could run actually estimates our parameter of interest. We'll get back to this example, but let's develop a more general framework first. We have an outcome variable y and a second variable x1 that causally affects the outcome variable. We don't observe x1. Instead, we observe another variable, let's call it x1 star, that proxies x1. We cannot run this regression. Instead, we regress y on x1 star and call the estimator from this regression beta 1 hat. For this to make sense, x1 star has to be indeed a measurement of x1. Specifically, let's assume that x1 star is equal to x1 plus some randomness w. And this w describes the difference between the proxy and the variable that it is proxying. So w is measurement error. We want to assume that x1 star is a good proxy of x1, in the sense that while measurement error exists, it is very nicely behaved. Specifically, we will assume that w satisfies the classical assumptions for measurement error. Before I discuss these assumptions, let's write down the linear regression model that describes the causal effect of x1 on y. Now, what are the classical measurement error assumptions? First, we assume that the expectation of w is 0. That means that on average, x1 star measures x1, because this part here is 0 on average. So in other words, x1 star measures correctly on average. Our next assumption is that w is independent in the sense of statistical independence. W is independent of x1 and the error term u from this regression model. This assumption says that there is no systematic mismeasurement, or intuitively, all mismeasurements that occur are honest mistakes. Our third and final assumption is that the variance of w is strictly positive, and this just rules out the case that w is always 0. If w was always 0, then x1 star and x1 would be identical, and there would be no point in talking about measurement error. So this assumption just says that measurement error exists. Let's apply this general framework to our example. So y would be the score on the econometrics exam. x1 would be ability. x1 star would be IQ test score. And the measurement error w would be, for example, how lucky you are on the day that you take your IQ test. Let's interpret the measurement error assumptions in the context of our application. The first assumption says that on average, IQ test scores reflect ability. The second assumption imposes two conditions. First, it says luck shouldn't depend on ability. So luck plays a similar role for everyone regardless of their level of ability. And the second condition is that w is independent of u. So here u can represent luck on the econometrics exam. So that says that how lucky you are on your IQ test is completely independent of how lucky you are on your econometrics exam. So if you're taking the two tests on 2 different days, then basically that says that your amount of luck should not persist. Then the last assumption just says that we have measurement error when we proxy ability by IQ. For the typical individual, the IQ test score does not exactly reflect ability. Our previous analysis of the properties of the OLS estimator doesn't apply to beta 1 hat here, because the regression model that we are estimating is different from the causal model that we are interested in. Let's write down both the causal model and the regression model. The causal model has x1 on the right-hand side. We cannot estimate the causal model because x1 is unobserved. For the estimated model, we replace x1 by x1 star. Let's pretend for a moment that we actually observe x1 so that this here is estimable by OLS. Can we estimate the effect of interest? Well, that depends on whether the causal model satisfies the appropriate exogeneity assumption. The appropriate exogeneity assumption would be that the conditional expectation of u given x1 is 0. Let's assume that this assumption is satisfied. This means that we can estimate beta 1 if we observe x1. Unfortunately, x1 is unobserved, so we have to go with this model here. What is the exogeneity assumption for the estimated model? The conditional expectation of the purple arrow term given the proxy variable is equal to 0. To assess whether this is a plausible assumption, we have to relate our estimated model to the underlying economic or causal model. And to do that, we'll rewrite the causal model. I'll start by adding beta 1 times the proxy, and that will be all right if I then subtract it again. By adding and subtracting, I haven't changed the causal model. Now I want to rewrite this part here slightly. And what is this? It's the difference between the proxy and x1. So it's just the measurement error. I have rewritten the causal model without really changing anything. So this is the same causal model that I had before. It's just a different representation. Now the only way for the two models here to be compatible is for u to be equal to this. Given this representation of u, it can be shown that the covariance between x1 star and purple u is equal to minus beta 1 times the variance w. We have assumed that the variance of w is strictly positive, so it's not 0. Now if we also assume that beta 1 is non-zero, so in other words that x1 has some effect on the outcome, then this here will be non-zero. Or in other words, x1 star and u are correlated. But if that's the case, then the exogeneity assumption here cannot hold, because if x1 star is correlated with u, then I can use information x1 star to predict u. So this implies that the exogeneity assumption does not hold. Or in other words, we have an endogeneity problem. To prove this equality here, the trick is to combine this representation of u with our measurement error assumptions. The details of the derivation are in the lecture notes. The estimated model has an endogeneity problem. Therefore, OLS estimation based on this model is not guaranteed to estimate the parameter of interest beta 1. So then, what does our estimator beta 1 hat estimate? Well, let's find out. So the first thing that will be helpful is that I've rewritten the causal model here. And now actually we have a model with two regressors, one of which is observed. I observe the proxy, and the other one, the measurement error, is unobserved. To make it easier to see that this is just a regression model with two regressors, let's define minus beta 1 to be beta 2. Now, a regression model with two regressors, one of which is unobserved, so that when I want to run a regression, I have to omit it. That sounds very familiar, right? Yes, because this is exactly the omitted variable problem. So the causal model here is actually equivalent to our long regression in the OV bias problem. When we discussed the long model in the context of omitted variables, we assumed that it satisfied the exogeneity assumption that is appropriate for a model with two regressors. In our case, this exogeneity assumption would be that the conditional expectation of green arrow term given x1 star and w is equal to 0. Is this assumption satisfied? Well, remember that x1 star is just equal to x1 plus w. So the information that I obtain from observing x1 star and w is the same information that I obtain when I observe x1 and w. Therefore, this is equal to the conditional expectation of u given x1 and w. So I have to determine whether I can predict u by using information in x1 and w. But I already know that information in w will be completely useless because of this assumption. W is independent of x1 and u. Therefore, the only question is, can I predict u from information in x1? And here I have assumed that I cannot do that. Therefore, the exogeneity assumption for the model with two regressors checks out. So the causal model is exactly like the long model in the OV bias problem. Now the estimated model is just the long model without the unobserved variable, right? So this is exactly equal to the short model in the OV bias problem. This means that we can apply our formula for OV bias. So the estimator beta 1 hat is approximately equal, at least in large samples, to the causal effect of interest beta 1 plus the covariance between the regressor and the omitted variable divided by the variance of x1 star. And this is multiplied by beta 2. We can rewrite this expression a little bit using the structure of our problem. For example, we know that beta 2 is equal to minus beta 1. Then under our classical measurement error assumptions, we can apply the rules for covariances to show that this here is equal to the variance of w, and this is equal to the variance of x1 plus the variance of W. Using these relationships, we can rewrite this part here as beta 1 times the variance of x1 divided by the variance of x1 plus the variance of W. Since all variances are strictly positive, this here will be a number between 0 and 1. This formula shows that our estimator does not estimate the causal effect. Instead, it estimates the causal effect multiplied by this. And since this is a number between 0 and 1, this acts as a scaling factor that scales down the causal effect. For example, if this is 1/2, then we're not measuring the full causal effect, but only half the causal effect. This kind of bias is called attenuation bias. It is called a bias because we are mismeasuring. We are not measuring the true causal effect. It is called attenuation bias because the effect that we are estimating is attenuated, that is, it is less strong than the true causal effect. Let's apply our new insights about attenuation bias to our economic example. We have our causal effect of interest, beta 1, that gives the effect of ability on exam score, and presumably this effect is positive. So it could be, for example, here. Now we have our estimator beta 1 hat that it is estimated from the regression where we replace the unobserved ability by observed IQ. In an ideal world, we would observe beta 1 hat close to the true causal effect. However, our formula for attenuation bias tells us that we will not estimate the whole causal effect, but only a fraction of the causal effect. So instead of estimating all of this, we'll just estimate a tiny fraction, maybe first 40% of this causal effect. And in that case, beta 1 hat would be somewhere here. So this estimator is mismeasuring the causal effect, or we can say it's exhibiting bias, and this bias is pushing it from the true effect down to here. Now let's suppose that in some other application, we have a negative true causal effect. If we have attenuation bias, we're not estimating the whole causal effect, but only a fraction of it. So we would estimate maybe this number. There would be bias again that pushes the estimator away from the true value up to here. So you can see in both cases, we're moving closer to 0 relative to the true causal effect. And this is why attenuation bias is also sometimes called bias towards 0. Bias towards 0 has two important properties. First, we will always estimate the correct sign. That is, at least up to estimation error. So it's impossible for these bias errors to extend beyond 0. You can see this easily from the attenuation bias formula. To flip the sign of the true causal effect, this here would have to be negative, but that's impossible because all the variances are positive. The second property is that we will underestimate the magnitude of the causal effect. In our application, this means that, at least up to estimation error, we expect to estimate the correct sign of the causal effect of ability. That is, we expect a positive estimate, but this estimate would be too low. It would underrepresent how important ability is. So in this video, we have learned that if we don't observe a variable of interest and we replace it by an imprecise measurement, that is a measurement that exhibits measurement error, then we will obtain an estimator that is biased towards 0. That is, it estimates the correct sign, but underestimates the magnitude of the true causal effect.